Well, good morning, everyone, and thank you for joining us for the Minnesota Stormwater Research Spotlights, part of the Minnesota Stormwater Seminar Series. My name is John Bilotta, and I'll be your moderator for this morning. I do want to just remind everyone you should be muted and have your video off, I believe. I just want to give you a little bit background about our Minnesota Stormwater Research Spotlights. We are highlighting research projects as completed through the Minnesota Stormwater Research Council. These spotlights are paired with our every other month Minnesota Research Seminar Series brought to us from St. Anthony Falls Laboratory in partnership with the Water Resources Center. You can learn more about our upcoming opportunities with the seminars by visiting our website. And as a reminder that all of our past seminars are recorded and available on the SAFO YouTube channel. More information about that is on our website again. So a few other details before we get into our featured presentation today. All of our research projects completed and ongoing are available on our website. You can easily navigate to either the current stormwater research projects or our completed research projects. As you look at the completed research projects, you'll find their final reports, appendices to information, and any past presentations. So please do navigate if you want to find out more information about the various research projects the Research Council is undertaking. I also want to extend an invitation to any and all of you to join us for our 2021 annual Minnesota Stormwater Research Council meeting scheduled for Thursday, July 15th from 8:30 to 1 p.m. Unfortunately, we don't have the guidance available to us to have an in-person meeting this year, so this will be virtual. But we do have a number of breaks throughout the morning to break up our screen time with all of you. Our annual meeting this year will feature updates from our 9 ongoing research projects this year. And we'll take a look at the year ahead for the Research Council, including the launch of our Stormwater Pond Research Strategy, our 2022 request for research proposals, and we'll talk about our efforts in technology transfer, including the next year of Stormwater Seminar Series. So please join us for our annual meeting July 15th, and I will put a registration link and more information about that in the chat box. Also, a little bit about our schedule for the next few months. Again, July 15th, join us for our annual meeting. And then our schedule for the third quarter will include our August Minnesota Stormwater Seminar Series featuring Jim Lenhart discussing underground systems. We do not have an actual date pinned down yet, so please check the website and all of you will receive an announcement about that as soon as we finalize that. September 16th, we will return to a spotlight on one of our council-funded projects. And I will just throw the caveat here. We may extend our time together with a council meeting, including a picnic. So just stay tuned for more information about our September seminar and council meeting. And then October 21st, we will welcome Robert Pitt to discuss biofilter media with us. So please join us in our future seminar opportunities. But that brings us to today's seminar. As we go through our seminar today, please use the Q&A function in the lower part of your Zoom panel to ask questions to the presenters. You may ask questions at any time during the presentation and give a thumbs up to someone else's questions, and we'll entertain as many of those questions as we can up until 11 a.m. So with that, it gives me great pleasure to introduce two great researchers, a part of our Research Council projects here. So go ahead, Heiko, and start sharing your screen. Our project and our seminar speakers today include Heiko Schoenfuss from the Aquatic toxicologist at the St. Cloud State University Aquatic Toxicology Laboratory. And his co-presenter and co-researcher is Dr. Richard Kiesling from the USGS. The project that they are presenting on is a project we funded as part of the 2018 research cycle, identifying source contaminants in urban stormwater and evaluating their removal efficacy across a continuum of urban best management practices. And this was a huge priority for the Research Council to look at the characterization of sources of contaminants in urban stormwater streams and how effective some of our practices are in controlling them. So with no further ado, I'd like to welcome both Heiko and Richard for their seminar today.
Thank you, John. I want to acknowledge my co-authors to start with. Richard Kiesling will cover the second half of this presentation. He works with Sarah Elliott at the US Geological Survey. And then my colleague at St. Cloud State University, Satomi Kono, who has done most of the molecular work that I'm presenting today. Next slide, please. Of course, a shout out to the Clean Water, Land and Legacy Amendment, which funded the research, and the Water Resources Center at the University of Minnesota for the grant administration, and also for providing a lot of feedback throughout the entire study. This was a very collaborative process, both between the agencies that work together as well as the Water Resources Center. Next slide, please. A quick outline of the presentation today. Again, we are going to split that between me presenting the first half and then Richard presenting the second half of the presentation. Starting out with a very simple question: why study urban stormwater? Isn't this a topic we covered 40, 50 years ago and thought we had solved? Knowing the topic of the seminar series, many of you are already familiar with the remaining and re-emerging problems, so this might be a little redundant, but for completeness sake, I want to just talk a little bit about the need to study urban stormwater before I introduce trace organic compounds, just to set the stage for the study that we are presenting today. And the first big objective, the meat of the study, which is to try to identify putative sources of trace organic compounds in urban stormwater using molecular techniques to essentially trace back to sources. We'll then turn it over to the resolution or treatment side, looking a little bit at best management practices that are present in Minnesota. And of course, and this is going to be Richard's topic, assessing the removal efficiency of trace organic compounds using those best management practices that are already in place. And we'll end, of course, with a few conclusions. All right, next slide. So again, this might be redundant to some of you, I apologize, but why do we study urban stormwater? Well, if we look at an image here of the United States, this is percent impervious surfaces, it becomes quite clear that especially in the eastern half of the United States, large areas are paved over, which means that any precipitation has to run via surface runoff, and a lot of that, especially in the big cities, has to be treated as urban stormwater, and it becomes an integral part of our hydrological cycle. Of course, we also have some places along the West Coast where that can be an issue as well. Next slide. On top of it, our urban population has been growing. It has been steadily growing since the 1800s. It's flattening off a little bit, but as the urban population is growing, more and more surfaces will be paved over. And so the urban stormwater problem is not one that's going to go away. In addition, next slide, we know much less about urban stormwater than some of the other sources of or pathways of contamination to our aquatic ecosystems. A lot of research has focused on municipal wastewater and its treatment prior to discharge into aquatic ecosystems. Of course, living in the upper Midwest, we're very familiar with the impact intensive agriculture, both row crop and feedlots, can have on nearby aquatic ecosystems, and a lot of literature exists on that topic as well. However, when it comes to urban stormwater, the knowledge base is much smaller, and so there's still a need to fill some very basic information, and this study was part of the effort of trying to fill in some of the gaps. Next slide. I said earlier, didn't we already solve the problem of urban stormwater? Well, clearly we haven't, but if we go back in history, at the early part of the 20th century, as urbanization really exploded in North America, we recognized that urban stormwater was something to be dealt with. And stormwater catchments were an early way to deal with the hydrology of precipitation in urban environments. But then in the 1960s and 70s, as the environmental awakening really happened in North America, we recognized that it was not just enough to buffer the flow of precipitation as urban stormwater. We also had to address some of the contaminants that were present in that stormwater. And of course, advancements in analytical chemistry in the 1980s and 90s really highlighted that PAHs, heavy metals, were a worrisome component of urban stormwater, together, of course, with sediments. It's only been in the last 20 years or so that we have come to recognize that there are many trace organic compounds, such as pharmaceuticals, personal care products, and even endocrine disrupting chemicals that find their way in urban stormwater into nearby urban aquatic environments. In a study that was done in Minnesota that we were part of a couple of years ago, we demonstrated that many of the compounds we associate more closely with municipal wastewater and its discharge are also found in urban stormwater. Next slide. So the trace organic compounds that we want to talk about today, the big classes, and this is not an exclusive list, of course, are pharmaceuticals, both over-the-counter drugs such as ibuprofen or acetaminophen or antihistamines, but also drugs that you only get by prescription. And again, at first glance, you would think, why in the world would we have to worry about prescription drugs running down our stormwater drains? We also see personal care products show up in urban stormwater. And again, the question arises, where are they coming from? And pesticides, something we usually associate with agriculture and rural environments, is also a big part of the urban environment. Whether it's the gardener that is treating his or her lawn on the weekend, or whether it is urban municipalities trying to deal with weeds along highways, roads, and parks, we actually apply a wide range of pesticides in the urban environment. And oftentimes they're not applied in as regulated an environment as you would find in agriculture. Next slide, please. So now a previous study that was published a few years ago, we actually took samples from multiple stormwater outfalls, both outfalls that went straight into the Mississippi River without any treatment, as well as several standard stormwater ponds and stormwater ponds that had iron-enhanced infiltration present. And when we first saw the data, and this is just a compilation of 2 sampling events, and then grouped together by different classes. So you can see, for example, the light blue color is pesticides, very prevalent in the right graph, and pharmaceuticals show up in this inflow in Maryland in the left graph. We were at first taken aback because the composition and concentration of these compounds, these trace organic compounds, really mirrored or were fairly similar to what you would find in a treated municipal wastewater effluent, and not something we would usually associate with urban stormwater. So we recognized that there was an issue, and trying to understand the sources became a big part of this current study. Next slide. Again, this might be redundant, but just to keep in mind that in most urban environments, with some notable exceptions, we have separated our stormwater from our sewer system. This has been a big effort that is still ongoing in some major cities. And the main idea behind it is stormwater, being episodic in nature, can overwhelm a sewer system, which would then lead to combined sewer outfalls and the discharge of raw sewage into aquatic habitats, which of course is something we want to avoid. So in most major municipalities, we have separate lines for sewer system coming from households and stormwater coming through stormwater drains. That of course means that we're dealing with 2 very different streams of pollutants. Sewer systems, everything that goes down our drains, but in stormwater, it is a broader range of contaminants that can find their way into this discharge. And because it's only episodic, it may build up over time. So every time it rains, we see runoff, of course, from roads and driveways, but also from sidewalks, green lawns that have been treated with pesticides, but also sources such as pets that might have defecated or urinated against the fire hydrant at the corner, or other sources that sometimes can be a little harder to identify. On top of it, we have to keep in mind that our sewer infrastructure is aging across the country. And so we are also dealing with sewer pipes that may be leaking and may infiltrate, therefore, sewage into stormwater pipes and stormwater conveyors. Next slide, please. So for the current study, we wanted to assess already existing best management practices that are being used in Minnesota, doing paired sampling between inflow, so water that is being collected from an urban area to run into a stormwater pond, and then the respective outflows, either in a standard stormwater pond, a straight outflow, so we're mostly dealing with sedimentation and then a clear water that is flowing out of the pond. But we also have iron-enhanced sand filtration, where the stormwater passes through an iron enriched sand substrate before it leaves the pond. And also for this particular study, underground infiltration basins, where urban precipitation is being captured and then underneath the surface of the roads and then allowed to infiltrate into the groundwater. Next slide. So to summarize where we are, we know that urban stormwater contains a complex mixture of trace organic compounds. And we also know from several studies that the concentrations can be strong enough to cause adverse biological effects. What we don't know is what are the sources of these trace organic compounds in urban stormwater. We obviously have some ideas, but that's not enough if we want to manage the resource of urban aquatic environments and treat those contaminations. And therefore, we wanted to also look at currently existing best management practices in the ability to remove trace organic compounds before the outflow from the stormwater pond then enters aquatic environments. And those are the two objectives. I will talk mostly about the first one. Richard will cover the second. Next slide, please. So here are a map of the Twin Cities. All of our study sites were located in the greater Twin Cities metropolitan area. You see 3 green cycles, one on the very top, 2 on the bottom. Those were stormwater ponds that contained iron-enhanced sand filtration treatment. The Birchwood site, the blue dot in the upper right, this is a standard stormwater pond that was something of a control or reference site for us. And then the purple triangles on the left side, these are underground infiltration basins that were also sampled as part of this study. Next slide. And if you want a little bit more information, I just listed this table. Again, we have 2 underground infiltration basins as part of the study, 3 iron-enhanced sand filtration ponds, and then our standard pond at Birchwood Park. Their watershed area differs a little bit. Some are smaller, some are larger. We try to get Birchwood Pond to be somewhat in between the different sizes, but that is, of course, one of the challenges working in an existing urban environment, trying to pair up different existing structures and gain information from it. So since the presentation is recorded, you can come back to this slide if you want more information. Next slide, please. Our sampling spanned the seasons, which of course in Minnesota is severe, and we need to keep in mind that stormwater has a very different consistency at different parts of the year. During snow melt, the ground is frozen. Many of our iron-enhanced sand filtration systems are not really functional as they're frozen. During the spring rain, we have very little vegetation that may serve as a buffer for the incoming stormwater. In the summer, the vegetation is at its greatest, but we also see that as the time of the year where pesticides are being applied at greater rates and people enjoy the outdoors, so sources may change a little bit. And then in the fall, everything kind of slows down a little bit. Next slide. Our sample collection followed USGS collection techniques. We had to become somewhat creative at some sites to capture either inflow or outflow. But in each case, we took multiple samples. So we had paired samples for the molecular work to identify sources and for the analytical chemistry to identify trace organic compounds and assess the removal efficiency through our best management practices. Next slide, please. All right, so to the first objective, how do we identify sources of trace organic compounds in urban stormwater? Many of these compounds can obviously come from different sources. And so we reverted to a technique that has been used extensively in recent years using environmental DNA. The idea being that you can extract DNA from the environment and then link it back to the organism that discharged the DNA in the process of urination or defecation or some other process that brought DNA in contact with water. So part of the water samples we would take at each site would be split off. They would be filtered through a 0.2 micron cellulose nitrate filter to separate environmental DNA from the water sample. The filtered water sample was then further processed to assess cell viability or the cytotoxicity of that water sample, seeing whether or not the water itself is toxic to exposed cells. And we did that because we were also interested in the estrogenic potential of these water samples. This goes back to prior studies where we have demonstrated that sometimes stormwater contains enough estrogen-like compounds, estrogens as in the female hormone, that it can actually activate estrogen receptor genes in exposed cell lines. Next slide. Starting with the cell viability, are the water samples toxic to cells? The answer is generally not. We saw very little cell toxicity. And when we saw it, our treatment did not make any difference. In other words, our paired inflow and outflow samples at all of the different sampling campaigns had comparable cytotoxicity. So we don't see that cytotoxicity when it was present, and again, it was seldom really severe. The ponds or the enhanced sand filtration or the underground infiltration basins did not affect cell viability or cytotoxicity of the water sample. Next slide, please. Looking at the molecular data, so here we used 3 commercial kits to assess the contribution of human environmental DNA, canine environmental DNA, and avian environmental DNA. In each case, we did some quality control work first. We used samples that were spiked with feces from one of those species or negative samples, and we compared them to standard samples that came with the commercial kit. You see there's a nice separation between negative and positive samples. In other words, if our kit, our water samples tells us that there is a positive hit for eDNA from one of those 3 different groups of animals, we can be reasonably assured that this is a true finding. All right, next slide. So here are the results, and this is combined for all species and all assays for our environmental DNA, the concentration of those in stormwater. We don't need to worry too much about the absolute units. You see there's some variability. All 5 of these sampling events are graphed to the same scale. And you can see they are higher in June and May than they are in September and March. In August, we have some variability between them. But what's important to point out is, once again, concentration of eDNA did not differ significantly between inflow and outflow for 4 of the 5 sampling events. The only exception is the September 2018 event where outflow samples differed significantly from inflow samples. Again, this is just all of the animals, all of the different commercial kits combined. I'll go into the details of what we found at each site in a couple of slides. Next slide, please. I mentioned earlier that in our previous studies, we had seen estrogenic activity in stormwater samples. And so we wanted to make sure we look at estrogenic activity, and we wanted to also see whether or not we could link estrogenic activity to eDNA for one of the groups of or genera that we were looking at, either humans, canines, or avian. We did see induction or activation of the estrogen receptor 1 gene. In some cases, a fairly good induction, a 5-fold induction of that. But there was no correlation to concentrations of eDNA. In other words, we cannot link the presence of estrogenicity to any particular source, a biological source of eDNA. And this is consistent with other studies that demonstrate that most of the time, especially in urban stormwater, estrogenicity is really the result of multiple sources contributing, and then the totality of that estrogenicity is what causes the biological effect. Next slide, please. Now, separating our different sampling campaigns. They're over the top. So between April 2018 and August 2019, the ponds are on the left side. Birchwood on top is the one that was our standard pond. And then we have the other ponds below. You have inflow and outflow. Inflow always the darker line, outflow the lighter line. And the first thing you notice, at each sampling campaign, we had at least one site where we got a hit on eDNA. Human eDNA was quite frequent. Now, again, going back to what I mentioned earlier in my introductory remarks, this is likely linked to the fact that we have an aging sewer infrastructure. And if you have leaks in sewer pipes, you may find raw sewage infiltrating the stormwater pipes. And this is probably where we get our hits from. We also saw canine eDNA quite frequently at different sites at different times. And here we're probably dealing more with the issue of urban habits and walking dogs around parks, around lakes, around stormwater ponds. A lot of those have walking paths around them. And even if the dog owner picks up the feces of their dog, the urine, which often contains pharmaceuticals, because many of our dogs and pets are these days treated with a wide range of pharmaceuticals, that urine will still find its way into aquatic habitats, including stormwater ponds. And that's likely the source of eDNA there. I want to highlight the September 2018 sampling event because we saw avian eDNA only during that event, but frequently at many of our ponds. And if you think about what happens in September, it is start of the migration of a lot of waterfowl from the northern latitudes to more southern latitudes. And oftentimes the ponds become, ponds and neighborhoods become places where ducks and geese and other avian species will rest and of course poop. So it's an important point to make because it means that we're dealing with different sources at different times. Now, how much do avian species contribute to our trace organic compounds? That's still an unknown. We know that through eating grass, pesticides in particular can be passed on, but probably less for pharmaceuticals and plasticizers and so on. All right, next slide. To summarize this first part, so we saw that urban stormwater does receive trace organic compounds through a variety of biological pathways. And again, the molecular analysis demonstrated clearly we're dealing with human, canine, and avian sources, and all of them have to be controlled a little differently. The problem is that the contribution differed by season, it differed by site, it differed by species at different times of the year. So it's a very complex set of sources, and addressing that can be rather tricky. And unfortunately, as part of our analysis of eDNA concentration, we don't see a decline in eDNA concentration through any of our best management practices. And so turning it over to Richard now, looking at the trace organic compounds and seeing whether or not we have the same pattern there, or if we are keeping the eDNA, but we're losing the trace organics. Richard, if you want to take it over, please.
Thank you, Heiko. Well, as Heiko has already pointed out, the work that we're going to be talking about is connected to extensive sampling on our BMP ponds and treatment through iron-enhanced sand filters and comparison to standard stormwater detention ponds. And the work that the Minnesota Stormwater Research Council funded focused in large part on the role of infiltration basins, and in this case, underground infiltration basins, and the comparison of inflow compounds coming in terms of stormwater and emerging contaminants, trace organic contaminants, into these underground infiltration basins, and the potential for those to end up in groundwater, as shown in the small graphic under number 2. I just wanted to point out that the sampling that continued under the Stormwater Council funding is tied to the work that Heiko just pointed out. The set of ponds, the subset of ponds that we continued to sample as part of this project are part of a larger group of ponds that were sampled under the companion LCCMR project that actually is wrapping up in the next year. The 2 infiltration basins are there at the bottom, and I'm going to provide a little more detail on those 2 basins. Essentially, our plans or our approach was to sample all of the ponds and the trace organics in the influent or inflows into the standard ponds, the iron enhanced sand filter ponds, and the underground infiltration basins, and then look at interstitial water sampled with mini piezometers in the margins of the ponds, and then look at groundwater sampled through observation wells in close proximity to the underground infiltration basin. The detail you see here are pictures of the installation of our UIB1 site in Minneapolis. And at this point, I want to point out the critical cooperation for this project, the Mississippi Watershed Management Organization and their partners at the City of Fridley and the City of Minneapolis. This particular installation you can see is a large box culvert with infiltration openings at the bottom. You can see that as it's constructed or laid in, it's surrounded by infiltration media. And the point I want to make here in the last panel shows the open port that's connected to that's the inflow port that goes through a grit chamber. There's one on either end of this installation. And we actually sampled inflow at both locations and then composited the sample. Some of the details of the construction are shown, or the design details are shown in the bullets. This has a slightly smaller infiltration area than the UIB2 that I'll point to in a moment. But it also gives you an idea what the design criteria are for phosphorus removal and TSS removal per year. The second site is of a very different design. Instead of a box culvert, we have a series of underground large structures and tubing. I believe they're approximately 4 feet in diameter. And you can see on the second panel where the information slide at the site shows the cartoon of the basic design drawing. Again, we're sampling downstream, if you will, of the inflow through the grit chamber and sampling just before it goes in to the treatment structure. This is at Summit Square in Fridley. You can see what the site looked like as it was being installed. And in the third panel, you can see our sampling truck and the observation well that we sampled. Again, the filtration area is a little bit larger than the previous structure, but both of them are fed by stormwater that's coming out of a collection system with an overflow that comes through a grit chamber and then into these underground structures. Notice also that this site had a number of partners spearheaded by the City of Fridley, who was very helpful to us in arranging for our sampling. So as Heiko already pointed out, we were looking at Trout Brook ponds and the Golden Lake pond. And I highlight Trout Brook because these ponds have been sampled for all 3 of our studies, starting with our collaboration with David Fairbairn at Minnesota Pollution Control Agency that first documented the reduction that's possible, or apparent reduction that occurs in these trace organic compounds between inflow and outflow from the sand filter benches. But it also shows the difference in seasonality here, early in a growing season and late in a growing season between the 2 ponds, shown here, the larger picture being of the Maryland pond, the lower picture being of the Jenks pond later in the sampling season. I do want to point out here that one of the enhancements that we were able to achieve in this design is we were able to add a observation well at the UIB #1 in Minneapolis through the assistance and funding from the City of Minneapolis. We then were able to add additional funding as USGS for instrumentation, including pressure transducers to continuously record temperature and water level, as well as precipitation rain gauges that were put in for the latter half of the study. And I just want to give a shout out to all of the people that helped in putting the work together for the UIB, especially folks at MWMO. Jen and Stephanie, when they were still there, were very helpful, and Stephanie was critical in identifying projects where we could sample. Uday, of course, was great in helping with the overall management of the project. And then at the City of Minneapolis, my colleague Shram, I want to give a shout out to him and his assistants. And then Minneapolis Parks and Rec were really helpful in terms of making our sampling integrated with theirs. So if we look first at the results for inflow and outflow at the ponds and how the pond data compared to the interstitial samples collected with mini piezometers, we'll notice a couple things. One is in all of the spring samples, there were greater detection frequencies in almost all of the compound classes here: pesticides, pharmaceuticals, semi-volatile organic compounds, and volatile organic compounds. There were more compounds detected in outflow than inflow. This was different than something we had seen in previous studies. But I want to point out that these data did not sample our other wastewater compound schedule, which would have included more compounds. And also, we're not sampling as many seasons here as we did in the work that was published in 2018 by David Fairbairn in our collaboration with MPCA and St. Cloud State. So there are some differences there in the study. Also notice that the difference between inflow detection frequencies and interstitial detection frequencies is quite dramatic across both spring and fall seasons. But now if you look at the fall detection across the, putting aside the Birchwood Standard Pond and looking at Golden Lake, Maryland, and Jenks ponds, you'll see that in the fall samples that our detection frequencies and numbers were greater in the inflow than in the outflow. So there still is a reduction in detection frequency, but it's concentrated primarily in the SVOCs, in the semi-volatile VOCs, and the VOC compounds, but really the SVOCs. Less so in the pharmaceuticals, and pesticides really didn't show the pattern. As Heiko said, pesticide detection in the stormwater flow is highly dependent upon season of sample. And I think you'll see some interesting results when we look at the UIB groundwater samples in some of the pesticides as well. I will also add that in this study, we actually were analyzing for more pesticides than we did in the previous work. And notice that pesticides were sampled at a higher frequency. There were more compounds in the pesticide schedule than, it's almost as much as the other compounds combined. The last point I'd make here is that volatile organic compounds, although certain compounds were important, there were very few detections, fewer compound detections. So in summarizing these results, we're looking at fewer than 10% of the compounds analyzed in total were detected in either inflow or outflow samples, and fewer organic compounds were detected in interstitial water than either of the other two categories, many, many fewer. Overall detections were similar in the inflow and outflow samples, as Heiko commented, but the fall inflow detections were appreciably larger than the outflow detections. Semi-volatile organic compounds and pesticides were the most common detections. And we didn't look at SVOCs in a previous work with MPCA and David Fairbairn, but we did look at pesticides, and this was also observed in our previous work, especially for late spring and or late May and then summer samples taken in July and August. This has always been the case. There were pharmaceutical compounds that were detected. It varied by sample widely, but 7 pharmaceuticals were detected in more than 30% of the samples. Most of these are what we would call lifestyle or compounds associated with caffeine and cotinine, which is a nicotine metabolite. But there were prescription drugs, metformin, and the antibiotic for the treats urinary tract infections. So going down now to the work that was done on the infiltration basins, you'll see us sampling here, one of the rain events at UIB1. And we're sampling through the access port there. You can see the Minneapolis Parks and Recreation ISCO sampler that we're sampling around. And our protocol here was to pump samples through Teflon tubing using a peristaltic pump and letting the readings stabilize, letting the water quality readings stabilize as recorded by a water quality sonde, a YSI Series 6900 sonde. And once we had stable temperature, conductivity, and dissolved oxygen, we then pulled our organic samples, our organic compound samples. And as I said, this is an example of one of the access ports for UIB1 in the city of Minneapolis. You'll see that down in the corner, there's that white plastic Teflon churn, and that's what we use to churn or combine the two subsamples taken at each access port. Samples were analyzed for VOCs, SVOCs, pesticides, and pharmaceuticals, as already outlined. Just to show the level of connection between the rainfall events here measured at first by rainfall from the airport, but from March of 2020 on, collected by tipping buckets at the two sites, UIB1 and UIB2. You can see that there actually is a relationship between groundwater level and rainfall events. The connection is much tighter. There's much tighter coupling between rainfall events and the groundwater levels at the UIB1 than there is at UIB2, and this may be reflected in some of the pesticide data that we'll show in a moment. The other point I want to make is that there was significant variation in rainfall at these two sites, so putting out the tipping buckets, the rain gauges, was important, with more precipitation observed at the UIB1 site than at UIB2 over the same period of time. Also notice that the groundwater response was faster and a greater magnitude at UIB1 than UIB2 for the same rainfall events. So if we look at the detection frequencies for the underground infiltration basins, comparing stormwater inflow with groundwater samples collected during the same rainfall events at those observation wells in close proximity to the basins, what we'll see is that we had higher detection frequencies in inflow than in groundwater. The combination of these compounds is intriguing, but notice that pesticides are still feature prominently in the number of detections, as do the semi-volatile organic compounds, the SVOCs, most of them PAHs in point of fact. Also notice that VOCs were of less importance in either the inflows or in the groundwater detections. But the real story for these compounds is in the concentration differences between inflow samples and in groundwater. And we're going to spend the next few moments looking at those results, first overall for all four categories of compounds, and then a little more in detail for pharmaceuticals. So if we look at the inflow results for both inflow and groundwater from the UIB sampling, you'll notice that there are some important differences. First, I want to orient you to the four panel graphs, and I want you to notice that the y-axis varies between these four figures. For example, down in the corner where it says farm for pharmaceuticals, concentrations on the y-axis range from 0 to 30,000 nanograms per liter or 30 micrograms per liter. Whereas if we're looking at the panel just above that for VOCs, the range in values concentrations go from 0 to 600 nanograms per liter. So there are significant differences in the total concentrations within these groups. If you look both at what we've seen in inflow and groundwater, it does look like that VOCs are showing up more in groundwater than in surface water. And notice that underneath the bar chart columns, that there's a number, and that represents the number of compounds that were actually detected that are making up this cumulative concentration. Notice that we're only looking at one compound in each of the VOC samples that were recorded with significant concentrations. Now look at the SVOC panel next to that for the semi-volatile organic compounds, and you'll see that we're detecting many, many more compounds. 55 SVOC compounds were analyzed, and in some cases we're getting as many as 16 compounds being detected in the inflow. But notice the very low detection, or the very low concentrations and lower detection rates in groundwater for the SVOCs. There's a similar pattern for pharmaceuticals, fewer detections, in general, fewer number of compounds. And then probably the one exception is in pesticides, where we have large number of compounds detected both in inflow and in groundwater, and at comparable concentrations, except at UIB1, but at UIB2, greater concentrations in inflow, much greater concentrations in inflow than in the groundwater itself. Also notice that there are large numbers of compounds detected in both the inflow and the groundwater. If we look at some of this in more detail, first of all, for the pharmaceutical, we'll see that there are similarities in the compound composition between the inflows shown in the first panel graph and the groundwater shown in the second panel. And again, notice the y-axis with very different concentration ranges. So we're looking at, again, 0 to 30,000 nanograms per liter, or 0 to 30 micrograms per liter for the inflow, and 0 to less than 200, from 0 to 200 nanograms concentrations in groundwater. So much, much reduced. Also, there's a general, more frequent detection of metabolite compounds in groundwater than in the surface water, stormwater inflows. But we do see both antibiotics and stimulants in the terms of caffeine and nicotine in both the inflows and the groundwater, most notably anyway at UIB1. And these were, as I said, these were paired samples, even though they're in two different panels of inflow and inflow and groundwater. So these are paired results. So in general, we're looking at fewer than 10% of the compounds we analyzed for being detected in either the groundwater or surface water, or the inflow or groundwater samples. And groundwater trace organic compound detections were less than 50% of the inflow samples. So we're detecting many fewer compounds in the groundwater. There's even greater difference in the concentrations, which I've already outlined. The SVOCs and VOCs were the most common compounds detected in groundwater. And there's a large variability in the number of SVOCs that were seen in the samples, but 16 of the SVOCs were detected in more than 30% of the samples, and most of them were PAHs. Finally, for pharmaceuticals, detections ranged from none to 9, with 8 pharmaceuticals being detected in more than 30% of the samples. If we look in more detail at what was going on with the pesticides, there were 12 pesticides that were frequently detected in groundwater, but the majority of these were actually observed almost exclusively in groundwater, certainly more frequently in groundwater than they were in the influent stormwater samples coming into the UIBs. And this is something we want to look at in more detail in the future, looking at the nature of these compounds and their use and how they might be found more generally in groundwater that's not necessarily responding to the stormwater inflow, but perhaps for other sources, more diffuse sources. So in terms of the next steps for the work that we've been doing, we're now comparing removal rates for the individual compounds that are the constituents in these classes that I've summarized for you today, and look at the detection frequency differences between inflow and outflow for both the ponds and for inflow and groundwater for the underground infiltration basins. We're also interested in investigating the differences in the pesticides that were more frequently detected in groundwater, as I already alluded to. We're also looking forward to a project where we are going to plan to test additional BMP pond treatment options in terms of the actual filtration treatment media through biochar or compost, looking at CEC removal as an augmentation of this work that we've done with LCCMR support, the Environmental and Natural Resources Trust Fund support in the past. And we're in the process of submitting a technical communication to a journal for the UIB results that I presented here today. Sarah Elliott is taking the lead on that. And this is in here to remind me to point out that Sarah has been the lead for USGS on this work. And the analysis that you've seen today is primarily Sarah's analytical work. And she's taking the lead on writing that up for the journal article. So at this point, I'll pause and see if Heiko had any more comments that he wanted to make, and we'll move on into questions. I think we have about 10 minutes left for questions. Thank you.
Thank you, Richard. I think in the interest of time, let's see if there are any questions that we can address.
Great. Well, thank you, Heiko and Richard. That was very fascinating and great research project. So we do have a few questions coming in. And so I'll take the first one here. Is it possible that VOCs are less present because they volatilize out of the water? Does this factor into your conclusions?
Well, the simple answer is that we don't know, but that seems like a reasonable mechanism. We obviously sampled following standard USGS protocols to avoid loss of the compounds from the sampling. So we think that the change reflects the real change in the environmental samples. One thing I will say that is that there was quite a bit of headspace in the UIB1 infiltration chamber. There was rarely water actually in the chamber. So infiltration was very quick. But I think there's also a lot of surface area there that would allow for volatilization within the chamber. There's a lot of airspace. I can't comment on the structure at Summit Square Park, the UIB2 site. So I don't really know what volatilization would be like in that system. But both of these have airspace so that if VOCs went into the chamber, yes, it's possible that they would volatilize and not be found in the water sample.
So another question that came up, Heiko, during your presentation is looking at DNA samples. Do you consider raccoon and other sources of wildlife DNA in your samples? Specifically with raccoon DNA, does it come out as canine DNA? Of course, we know that raccoons find shelter in storm sewers. So what at all is their contribution?
That's an excellent question. I think there's a whole bunch of things living in storm sewers, alligators too, if you go to the right place. But I think the commercial kits we use are species specific, so, or at least genus specific. So I would not expect raccoon or rat DNA, as another example, to really factor large into the conclusions that I presented or the results I presented. Now, in the case of avian DNA, for example, obviously there would be some other avian sources as well, but raccoons are probably not gonna show up strongly in either one of our commercial kits.
All right, next question about pesticides. Are the pesticides you are detecting in groundwater commonly used for lawn care in the urban areas? Do you have more specificity about the pesticides?
Well, the inflows certainly reflect, the inflow stormwater samples reflect domestic use or residential use as well as commercial use. I mean, there's overlap between the two because the area that we sampled, although it had a UIB1 had a high percentage of impervious cover, there actually are still lawn areas that contribute to the runoff there, and it's possible that that's part of it. But the site around Summit Square was very residential and had quite a few pesticides in the inflows. The compound, I know less about the pesticides that were detected in the groundwater. And again, they're at very low concentrations. So at this point, I'm going to have to punt on that a little bit and say that I'm not sure that they're actually all for residential use, but some of them are. Certainly, simazine is in some commercial preparations that are used in by homeowners. And I will actually say that there were a number of other simazine or triazine, not simazine, but triazine and atrazine compounds detected in the inflow from residential use. So I guess what I'll say at this point is that some of them reflect residential use, but I need to know more about the use profile for those particular pesticides before I'm going to commit to saying that's the actual source of the compounds. And also note, and I tried to touch on this, that there's less direct relationship between the rainfall events and the response in groundwater levels at the Summit Square site, suggesting that there might be a more regional or larger area response for recharge influencing the water levels at Summit Square. And so I hesitate to make a strong connection between what we observed in stormwater inputs at that site and what we're seeing in the groundwater. It would take additional groundwater work. I am not a groundwater hydrogeologist or hydrologist, and we've talked about that with some of our colleagues, and we hope to explore that in more detail in the future.
And Richard, if I may follow up on that, from our broader previous and ongoing studies, we have seen a number of more agriculturally based herbicides in particular that show up in urban stormwater. If I look at our previous studies, so atrazine, some of the row crop pesticides that we're dealing with in rural Minnesota also show up in the urban environment. And to echo what Richard said already, the impact that we're seeing on urban stormwater may be more regional than the watershed that is being drained by a particular stormwater pond would predict.
Yeah, I guess I kind of was a little, I might have been a little obtuse there, but some of the compounds like atrazine are now being used in domestic or residential preparations. And then if you have commercial applicators, they are using some pesticides that you might think were more agricultural in origin, but they're using them in an urban setting. For example, if you have pesticides applied to trees on your lot, many of those are restricted to certified applicators. They may not be over-the-counter sales to homeowners, but they're being used in a residential setting. So that's why I was hedging my bets a little bit on my answer. So.
Thank you both. We have time for two more questions. And I see there's some interest here on groundwater. I think, Richard, you started to touch on this in your previous comments here. But it looks like the results are initially encouraging for groundwater impacts from stormwater infiltration. We don't have as many impacts as maybe would have been guessed. So you can comment on that. And then did you evaluate for any groundwater samples, i.e. shallow urban groundwater far from an infiltration practice that might be coming in?
No, we did not compare. Let me answer the second half of that first. We did not compare the groundwater samples that we collected in close proximity to these underground infiltration basins to a control or to samples from an observation well that was farther away from the UIBs, perhaps maybe in the same land use or land cover class, but not influenced by the UIBs. So no, we did not do that. And that was kind of what I was getting at with my comments about the Summit Square location. We also did not do any tracer studies, dye studies, to measure the degree of connection between infiltrate coming through the UIBs and what occurs in groundwater. We did do some chloride sampling, but it was not extensive enough to try to connect those two. So. And then the first part of that question, I think it related to the overall concentration. I would have people look at the graphs and see the very, very strong differences in total concentration between inflow and then what we're seeing in groundwater. Very reduced concentrations. Not sure what the mechanism is. Could be abatement of those compounds or it could be dilution, but there's a big, big difference.
Well, great. One last question, but first an observation. I see a few of our advisory board members for the council are online with us today, that we can look at these research results with Dr. Ishii's work in the compounds that he's detecting in stormwater reuse systems. So I think these will be two great studies to combine together and see what results will be. But Richard and Heiko, for our last question, I think suitable for us to end on here is, what conclusions can be drawn from your work, especially conclusions that can lead to appropriate actions and management recommendations in our communities across the state and across the country?
Oh, wow. Okay, that's a big one. I think the first thing, if I may start, is that we have to really identify site-specific conditions. If we especially look at the eDNA component of the study, we saw the very strong impact of canine eDNA at certain sites and certain seasons. So if I think about some of the urban lakes that are surrounded by walking paths or urban stormwater ponds that have become part of the urban recreational landscape, we can probably put in buffer strips like rain garden type buffer strips to really mitigate the effect of this runoff from, dog, especially dog urine, going straight into the stormwater. So if we have a buffer in between, a vegetation buffer, and we don't just run off that urine with the precipitation event straight into the stormwater pond, we might be able to really reduce one particular source. It also clearly hints at the need to repair our ailing infrastructure. We all know that. I know there's political movement in Washington to address that on a larger scale, but it is clear that stormwater carries a portion of municipal untreated sewer water, and I think that needs to be addressed if we really want to get to the issue of stormwater. I'll let Richard finish that answer.
So one of the things I work on is the occurrence of these compounds, of trace organic compounds, and commonly referred to as contaminants of emerging concern, in the margins of lakes, in lakes. And Heiko and I have, and our colleagues have collaborated on that issue. And it actually appears that stormwater is, at least especially for urban lakes, but maybe even for suburban and even some ex-urban lakes, is a potential source of these compounds getting into the margins of lakes. And there's potential biological impacts of that. So we do need to be focused on effective treatment measures. I think we need to continue our investigations in the potential for treatment and removal of these compounds in these passive treatment systems using iron-enhanced sand filters or other treatment media, and think about how we can distribute that in the urban landscape and at a watershed scale to prevent these compounds from getting into surface water.
Heiko, that's fantastic work and a great presentation today. For all of our participants, we will send all of your questions to both Heiko and Richard for some additional follow-up. So in the meantime, a round of applause to both of you. Thank you for sharing your work. Just as a reminder of our upcoming seminars here, join us for those. We'll have more information about those about a month before each of those dates. So thank you all for joining us again this morning, and have yourself a great rest of the day.